And let's move into a little bit of trigonometry. Just I don't know what the good phrase would have been there. Okay, so we got sine theta is minus 4 over 5, tan theta greater than 0, and it's just, without the use of a calculator, 8 of a diagram. The way it's structured here, it's just crying out for one particular way to solve this. Remember, there are many ways to solve these types of questions, but there's one that's really sticking out and saying, well, let's draw our beloved cast diagram. Do you remember how often we used our cast diagram? So we had a set of axes, x and y, but really we don't care about the x and y. It's 0, 90, and we know in the background the CAST, remember it right? Cast, CAST, all are positive here, and then anti-clockwise, because everything's anti-clockwise in mathematics. Well, not everything, but this does. Unless then when you get to bearings, remember, then what was all that about? Okay, we've got some things, tan theta's greater than 0, and sine theta is less than 0. Okay, so where's sine theta going to be negative and tan theta positive? Which quadrant are we working in? Well, definitely not in the first quadrant, because they're all positive. So let's find out where else tan is positive, and there it is. So let's draw our not to scale diagram over there. There's our triangle. We know that's a point xy, and we know that r equals something, right? So you can get into the question. Cool. I'll leave you to do the rest and pick up your present on the way out too. Where's the rest of the bow? There. Okay. What else do they want us? Sine 90 plus theta plus tan theta. Okay, well, tan theta is going to be easy enough, because we know our tan theta, either you've gone in the background, you've got your SOHCAHTOA, and then you're like, tan is opposite over adjacent. What was it? Opposite over adjacent. So tan was like y over x. So, and by this stage, we've got x, y, and r. Sine 90 plus theta. What do we need to do to this? Well, let's reduce it. Reduce, yeah, that one, right? So 90 plus theta, I think it's handy. I wish we had some more space here sometimes. So you could just go, cool, we've always got our cast diagram for handy. Sine 90 plus, we know must be sitting in this quadrant up here, because there's 90, so 90 plus must be there. The 90 plus minus everything to 90, those change to cos, so that's going to be cos theta, and we just need to decide, is it going to be positive or negative? So we look at the original function, was sine theta positive or negative over here? Well, sine is positive, so it remains positive, because this was positive. This is a positive value. It's in this quadrant, so therefore this should be a positive value as well. So cos theta, so you can work the rest out, plus tan theta. You've got your x, y, and r's, so just do everything. We already said that was y over x. Cos theta, sub in the calculator, poof, and you get there. Okay, what else do they need from us? Simplify the following without the use of a calculator, which means we'll have it handy just in case, and to a single trigonometric ratio. Cool. So remember what the idea was for these ones. Yeah, definitely a cast diagram. Always do one, and you can definitely have one and then draw another one maybe if that one gets a bit messy. But we've got cast for reference, and and as I said, maybe just another scribble if we need to. It's very like naval and like sea, like with the blue and the yellow, right? So let's see. Sine 330. So the idea was, oh, where's 330? 330 is here. Well, it's cos, so therefore it's going to be negative. And well, if that's 330, then this bit here is 30. So that's going to be, if we're going just to the 180s and the 360s, that still stays a sine. So that sine 30 is a positive or negative. Well, sine is negative here, so it has to be negative. Tan of negative theta. That's the idea behind this one. Tan, well, the way is negative theta. What is our strategy with the negative theta? we always just added 360 most of the time. Then we could go, oh, well, 360 minus theta is sitting, I'm going to do it in this diagram here. So it's sitting down here. So 360 minus theta is down here. So it must be negative. So therefore, that's going to be times negative tan theta. That was our idea. So keep going with the rest of those. Cos, where's cos, blah, blah, blah. Let me stop before I do the whole thing. That's the idea behind that one, which we know. Ooh, diagram shows these things, and let's finish this off. Diagram shows the graph of f of x equals cos 2x for x an element of 0 to 360. There we can see x goes from 0 up to 360. That's that part. We've got f of x, this thing here. Ooh, wow, great highlighting. Is cos 2x. So really the thing is, what is, let's remind ourselves of a few things. Putting the 2 there, what is the effect of that 2 compared to, say, y equals, let's not do it in the same color. What is the effect of that 2 compared to y equals cos x? Well, the 2 changes the period, so it squishes it. Notice that y equals cos x would have gone here and here and here and would have fitted in just once. Whereas y equals cos 2x, here it is, and then again. So it's repeated twice in that time. So that's what our 2's doing. Sketch the graph of g of x equals 2 sine 2x for x an element of 0 to 360. Cool. So we're sketching it for the same domain. So that's our domain. It stays the same. So basically sketch it in that 2 sine 2x. So we already said what this 2 does. It's going to fit 2 sines in it. And then we're asking ourselves, well, what's the effect of this 2 here? What is, if you multiply any function by 2, what does it do? It stretches it out by 2. So instead of sine x, if we add it for reference, sine x looks like that. So it's going to start here, but instead of doing that, our graph is going to go, and we said we're multiplying by 2. So that's what that's going to do. And so that's the effect of that 2. And the other thing that's going to happen, let's do it in this yellow, this 2 says that it's going to repeat twice as often. So therefore, we know we're going to start there. And instead of just going like this and going, oh, cool, there we go. Oh, that is actually what it looks like. Instead of going like there, yay, there's y, this would be y equals 2 sine x. You need to squeeze it in 2. I'll leave you to do that though. Otherwise, we're really just doing the whole thing. So note that this is not the answer. This is y equals 2 sine x. But I'm just drawing it there for reference. And you're going to squish it in twice. That does seem right. Determine the x values of the points of intersection of the 2 graphs. Well, how do you find the intersection of 2 graphs? We'll just put them equal to each other, right? So we've got this one here, cos 2x. So we've got cos 2x, and just say, well, when is that equal to this one here? I'm purposely trying to avoid that red-green combo. 2 sine 2x, when are they equal to each other? Cool. And you solve from there. But wait a second, let's just help ourselves get there. We don't know how to solve when it's 2 different things like this. So what can we do to our equation so that we just have a single trig ratio? Well, if you divide them both by cos 2x, what's sine over cos? Well, it's just tan. More correctly, sine theta over cos theta is tan theta, but we could simplify this to tan theta, and therefore that's just going to be 1 equals, and then you're working with tan theta, and then you're finding general solutions. So there's going to be a plus k, and we did it. Our version is going to be slightly different to the memo for this year, because there's got a k180, we went plus k360. We've got two different solutions, and then find out which ones actually are between 0 and 360. That'll be a nice interesting one to do. Okay, that is that for now. Ooh, identity's up next. I can't wait.